Hello, this is part 4 of Electrical Circuits tutorial series. Today we'll be discussing parallel circuit rules and parallel circuits. So parallel circuits have a set of rules just like series circuit had their set, and we have to abide by these rules. We can't violate them or else the circuit will not work. Note there on number 6, the power rule, the sum of the power dissipated by individual components equals the total power. That holds true for all circuits. Doesn't matter what kind of a circuit it is. So that rule applies to a series circuit, a parallel circuit, and also to a series parallel circuit. Now, a good example of a parallel circuit would be in a department store or grocery store. All the lights that they have in the ceiling. We have 2 or more paths for the current to flow. So if one of those light bulbs go out, the rest will continue to burn. The only difference is they have changed values. And so that's how you can tell a parallel circuit. Now we'll be using this parallel circuit. Remember, this is the cell symbol that we're using as a battery to save real estate. Remember, the longest bar is always a positive and the shortest is always a negative. So always pay particular attention to how that battery is put in there, how that cell is put in there. If you'll notice, if you remember from the series circuit, I have flipped the battery over in this case. Then we have our first load here. Remember, that's a resistor symbol. We have our second load here and our third load here. So the way that we tell that it's a parallel circuit is we trace this circuit. We have one path up to this point right here. That point right there is called a node. That's where 2 or more wires are joined together. So we have a path here or we have a path here. We come to another node, so we have 2 more paths, one up there, one up here. And then we go through our last load and come back. They all join in together with another node, full circle back to the power source. So in a series circuit, we call them series strings. In parallel circuits, we call them parallel branches, and this is a 3-branch parallel circuit. We'll be using ear and pie thumb wheels we discussed in part 2, and then the parallel circuit rules that you just viewed. So in a parallel circuit, it's a little bit opposite from what the series is on some of our rules. And the parallel circuit, our current is the sum, total current is the sum of the individual branch current drops. And so we can say I sub t is equal to I sub 1 plus I sub 2 plus I sub 3. And in this case, the example we're using here, I sub 1 is 8 amps plus I sub 2 of 12 amps plus I sub 3 of 4 amps, giving us a total circuit current of 24 amps. Now, for our voltage in a parallel circuit, the voltage remains constant across all branches. So we can say V sub t is equal to V sub 1 is equal to V sub 2 is equal to V sub 3. In this example, we're using 120 volts. Now, our resistance is a little bit different. Our parallel circuit resistance rule states that the total circuit resistance will always be lower than the lowest branch resistance. There's 3 methods we can find this. The first one, every branch has to have the exact same resistance. That would be resistors of equal value. And the way you use that is if every branch has the exact same resistance, you can take the resistance of one branch and divide it by the number of branches to get your total resistance. Another method that there is, and it works quite well if you only have 2 branches, is our product over sum, which would be R sub 1 times R sub 2 divided by, open your parenthesis, R sub 1 plus R sub 2, close your parenthesis. The problem with that is if each additional branch you add in, you have to do another calculation. That's more of a margin for error, room to make a mistake, back finger something on the calculator. So it's ideal if you only have 2 branches. It is backwards compatible, and you can use it where you would use the resistors equal value. And the third one which is most used, especially for those first learning, is the reciprocal formula. What that is, it's a 3D formula, and it's 1 divided by, open your parenthesis, 1 divided by r sub 1 plus 1 divided by r sub 2 plus 1 divided by r sub 3, close your parenthesis. So it's a reciprocal of the reciprocals, basically, is what we're saying. And so in this case, we would do 1 divided by, open our parenthesis, 1 divided by r sub 1 of 15 ohms, plus 1 divided by r sub 2 of 10 ohms, plus 1 divided by r sub 3 of 30 ohms, close the parenthesis, and we come out with a total circuit resistance of 5 ohms in this example. And as you notice, it is lower than the 10 ohms, so it meets our circuit rules. Now our power formula, again, doesn't matter what kind of the circuit is, it's always the sum of the power dissipated by the individual components for your total power. So we can say P sub T is equal to P sub 1 plus P sub 2 plus P sub 3. And in this case, the power of our first load, P sub 1 is 960 watts, P sub 2 is 1,440 watts, or we could say 1.44 k-watts, and then R sub 3 is 480 watts. So we add all those together. Now, when we write our answers, if you see up there in the schematic, you see it's 1.44 kW. But down here, we put it out in full standard decimal. That's so that we get our decimal place in the correct position. And this circuit would have 2,880 watts. And we would designate that as being 2.88 k-watts, kilowatts on that. Here's the zoomed in view of the circuit with all the values going to which each one goes to, and as you can see, they all follow the circuit rules. Thank you for joining us. That's the end of part 4.